Hey guys, I'm doing another video here. Um, you'll see currently that you are viewing something microscopic. These are actually cells in an onion peel. You can see those dark borders around it. Those are the plant cell walls. And then there's a membrane that's pressed up against the plant cell wall there, which you can't see, but you will see in a moment with this video that I'm going to do. This video is going to be relatively short, and I am freestyling this video. This is not a prepared one. I'm currently in the process of taking an anatomy exam, physiology exam, and an EMT exam. I'm very busy. On top of that, I think there's a good chance I might have contracted COVID at my CNA job. Just running a fever for the past 2 nights and just haven't been feeling good. But I wanted to put something up, and this is something that I can probably just kind of comment on and show you guys the process behind it and how it can affect the body in certain ways. So the topic is osmosis, which you have probably heard about before, I would imagine. Excuse me. I will be coughing occasionally throughout this video. Please bear with me. All right. So normally I would do some explaining first before I actually started showing something like this, but as I'm very new to doing these videos, I didn't want to sit and explain something for 5 to 10 minutes and then bring my phone over to my microscope here and not be able to get it to work, or something weird happened and then all that time be for nothing, and because I just don't know how to put videos together yet to make it one continuous thing. So I am going to show you this and kind of explain what's happening, and then I'm going to go to the board here and bring the phone up and kind of show you guys how this affects the body in a couple ways. So when it comes to cells, there is different types of what we call tonicity or tonality, and an isotonic tonicity is healthy. That means that the pressure on the outside is equal to the inside. And that's actually what you're examining right there, and that's actually what you want the cells in your body to be. You want them to be isotonic. If you have a hypotonic situation, the cells will actually get really large and engorged and will go through a process called apoptosis, which is cellular death, and they will literally explode. And if you have hypertonic cells, the water will actually leave the cells and will shrivel up. Dehydration is a big one when it comes to that. If you're not getting enough water, your cells will undergo a hypertonic state and the water will leave. So because I only have so there's a difference between animal cells and plant cells. Animal cells don't have a cell wall, so they're able to explode if they get too big. Plant cells actually do have cell walls, and those are all the dark borders that you can see. And those actually prevent it from totally exploding. Plants undergo a lot of pressure. Actually, in plant biology, it's called the level of turbidity when you're looking at the pressure against the cell wall. And that's actually what causes the plant to stand upright if it's in a humid environment, because there's so much pressure on those cell walls and it causes the plant to stand. And vice versa, if you're in really dry climates, the water will leave and will shrivel up, and those cell walls won't have pressure against them, and then the plant will kind of droop over. You see that process all the time. So because this is a plant, I can't show you a hypertonic situation, or excuse me, a hypotonic situation where the cells will explode, because the cell walls there are going to protect that from happening. But I can show you a hypertonic situation. Now I want to show you this, just kind of show you what it is, and then after I do it, I'll take you to the board and I can explain what's happening and how it applies to certain parts of the body. So to look at this, I'm going to stick a hypertonic solution onto the cells. Basically what that means, well, I'll just skip that part. I'll explain what's happening on the board. Let's go ahead and just stick this under. I'm going to take the scope off of this for a sec so I have room to stick this special water on. So bear with me, it's going to go dark, and I'm going to stick this with my syringe without spilling over and getting onto my lens. Okay. All right, we're going to go back here and see if we can see this process undergo. Let me refocus this. Okay, now you'll see, it looks like you're seeing a couple things moving there. That's just it moving through the water solution that I put on there. Okay. Let's see here. All right, sometimes this takes a moment, but what we should see is the borders, the cell wall borders start to thin, and then you should see a very thin line on the inside of the dark borders, which is the cell wall being pushed or pulled away, or excuse me, the membrane being pulled away from the cell wall. So this is why I wanted to do this part first, because I don't know if I can get a good image of this occurring. Let me move this around here. See if I can see some action. Oh, there we go. I think that might be good there. You see how thin it is right there in that area? That's because the dark areas that you typically see, those dark borders, that's actually the cell wall and the cell membrane together. And you see these ones here are super thin because the membrane is being pulled away from the cell wall. Nope. That's not, well, it is a little bit thinner, but not too much. All right, I'm going to look around a little bit more here. Refocus. Okay. All right. Nope. We're going to try a different type of onion cell here. We actually do the one that I'm using here is actually the purple peeling on the outside. We actually typically use the white part of the cell. I was choosing the purple because I figured you guys would see it better. But for one reason or another, outside my area of knowledge, that is not working. So I am going to go back to getting this white part of the onion, and we'll give this a shot. With how long this is taking, I'll just kind of explain a little bit. So this solution that I put on has a lot of salt in it. So every solution that you have, you are working with solvent, which is the liquid portion, and solutes, which is the particles inside of the solvent. So in this case, we're working with water and with salt. So salt would be the solute and the water would be the solvent, and together it makes a solution. And solutions that have a high rate of solutes will pull the water from the cells. Okay, let's see if we can see something. Let's come over here. Okay, here we go. Different layers. All right. Now you can kind of see that there's different layers of cells in this thing. It's very difficult to get a single layer. Okay, there we go. All right, I'm going to put this right in the center here. Sorry, this took so long. Okay, I am not an expert at this. Okay, so right in the center there, you'll see a circle, dark band, and then you will see a light circle on the inside of that. Really quick, I'm going to zoom down because I want to make sure that that's not like another cell underneath it or something like that. Okay, yeah, so that's definitely a cell wall there. Okay, I'm actually going to see, it's going to be kind of interesting, see if I can make a pointer with a hair follicle, or excuse me, not a follicle, but just a hair. Where is it? And point at this. It's kind of funny. Oh, you saw it pass. Right there. Okay. Well, it's pretty difficult to actually make this. Okay. Right there on the edge, it looks like I'm squishing it. Like I'm squishing the onion cell that I'm trying to show you guys. So that, you see the dark border around it, and then you see the circle on the inside. So that circle on the inside is the cell membrane shrinking. That's so cool. I love looking at my microscope and seeing these things. I've looked at my blood and many different things, a lot of cool things. I'll have to show you guys blood sometimes. And actually with blood, I could show a hypotonic situation, and we can watch the blood cells actually explode. I might do that sometime when I get the nerve to stab myself. I just wasn't really thinking about it. All right, so I'm going to take you to the board and kind of explain what's going on here. Let me see if I can pull this out here and make this stand. Okay, why are we blurry? I think I got a little click. All right, there we go. All right, I'm gonna get my markers here. Okay, so this is osmosis. This is the process that we're looking at. So you have, the cell is isotonic, the cell is normal. I'm going to use a red blood cell here, okay? This is the slight indentation on the inside of the red blood cell. It has kind of like a bi-indentation on both sides. So this is isotonic. That's healthy, okay? So in a healthy cell, and in all cells in general, actually, let me do another big cell down here, okay? This can represent any type of cell. I'm not going to draw anything in it because I got to show you guys something. So in cells, you have potassium on the inside, okay? It's heavy on the potassium on the inside. So do potassium, okay? I'm not going to get into the chemistry behind it. Just know that potassium has a positive charge. That's why I put the plus there. And on the outside of cells, you have sodium, lots of sodium, very, very high concentration, okay? Na plus, okay, lots of sodium. The way I like to try and remember this is think about a banana. People generally know that a banana has potassium on the inside of it. So there's potassium inside the banana, and then you're putting salt on the banana. I don't know why you would ever have salt in a banana. It's disgusting, but you generally put salt on your foods. So just thinking about that helps me remember. This is actually one of those things that people always forget which way this is going. So in an isotonic solution, the pressure between the inside and the outside is equal. Let me do another one here, okay? So in hypotonic cell, it's going to be really blown up with water, okay? And it will eventually explode if it doesn't get relieved. It will kill and go through apoptosis. So I'm going to write that word down because that's an important word here. Apoptosis. Cellular death. Okay. And if we have a hypertonic, which is the one that I showed you guys, hypertonic cell, we have a shrinking. So if it's just an animal cell, like within us, it's just going to shrivel up like that. With what we observed, because there was a cell wall, we had something like this, and then you saw the cell membrane pulling in. So a little bit different with plants versus animal cells. All right, so with the solution, let me use this here. So a solution, I wish I had a bigger board. I'm probably gonna have to end up erasing some of this stuff. A solution has solutes and a solvent, okay? The solvent is the liquid, and the solute is the molecule, the ions, just whatever is in it. It can be multiple things, okay? So I'm just gonna put particles. Just a way to encompass everything that I can possibly think of, okay? Okay, let's think about this. Make sure that I'm showing you guys everything here. Here's my okay. So okay, oh man, I'm trying to think about how to explain this at the top of my head. Like I said, I'm going off of memory here. I've not prepared for this video. So when you have a high solute solution on the outside of the cell, everything is going to want to equalize on the inside and the outside. It wants the pressure, okay? Different things will affect that, like the charge and then the actual pressure itself. But so if you have this high solute, hypertonic solution on the outside of the cell, it's going to want to equalize. And actually, I just thought of something. I can show you guys how this works here in a sense. Let's say that I had a bucket and it was separated by a semi-permeable membrane. Now, semi-permeable is actually the membrane that's in our cells, okay? And what I mean by semi-permeable is it's going to allow the passage of some things and it's going to block other things. It will allow the passage of water, though. So if I have particles inside of this solution here, okay, a lot of particles. And then I stick in a lot lower volume of solution here, and this one has a super high concentration of solutes, okay? All right, so this is a lot more concentrated. It's going to want to equalize the gradient or the difference between the solute versus the solvent. So the concentration is going to want to make it the same. So this semi-permeable membrane is going to allow the passage of water into here to make it equal, okay? So the level of the water might end up being different. So the water might come up to here, okay? And then this might drop down to here. The level of the water isn't what equalizes. It's the concentration. I mean, it could equalize, but what it's trying to do is equalize the concentration. All right, so they're equal on both sides. And that's what's happening with osmosis. So even though they're different solutes, the concentration is not even, okay? And it's gonna want to try and even that. So water, let me get a different marker here. Let's see if my green one will work. Will exit the cell, okay? So H2O is leaving, Okay. And when water leaves the cell, it adds more to the outside, and it will help equalize the concentration gradients between the outside and the inside. And of course, as I've already shown, this is what happens. The cell will shrink. And this is osmosis. This is something that happens that's constantly being regulated in your body. Okay, so I'm going to kind of show you guys some ways, some medical things that we actually see in our body and what happens. Oh, oops, I totally forgot to get my eraser. To be honest, I have no idea where it is. So I'm just going to use my hands really quick. Leave that part up there. Okay, so some things that this will affect. If let's say you were stranded out in the ocean and you didn't have any water, so you decided to start drinking seawater. So as I showed you with salt, okay, that's a solute. So let's say that this is a layer of cells inside your intestinal tract. Okay, here's a layer. Here's the layer on the other side. Okay, we're going to kind of do these. These represent individual cells. Okay. And then you decide, oh, I am dying of thirst. I've been stuck on here forever. I'm just going to take a risk and start drinking the seawater. Okay, so salt water is going to come into here. Okay, I'll just kind of do a little flow here just to show that it's going through. And it's going to pass through your digestive tract. And it is extremely high in sodium. Obviously, it's salt water. Okay, so these represents ions of Na, sodium. Now, the cells inside your intestinal tract also have water in them, and they have potassium inside the cell. Obviously, they have more than one potassium ion, but these are small and don't got a lot of room. So it's going to try and equalize the concentration gradient. So water is going to start exiting these cells to try and equalize that. Okay, and it's still not going to even come close to equalizing it with that much seawater coming through your system. It's going to attempt to, and these cells are going to start to shrivel. Okay, and on top of that, all that water from your cells is going to leave your intestinal tract, and you're going to have severe diarrhea, dehydration, and most likely death if you're not able to turn this around. It will kill you. So that's a case in which drinking water could kill you. So think about that if you ever get stranded out in the ocean. Okay, sorry guys. All right, I'm going to erase this here. Come up, draw another thing here that happens. Another cool thing that might happen is inside your blood. I'm going to do, how do I want to draw this? Oh, I wish I had a red marker for blood, but I don't. Let's say you have a vein here, or an artery, right? Arteries go away from the heart, veins go towards the heart, okay? So we'll just say we're working with an artery, it's going away from the heart. Now, blood is made up of plasma, which is further subdivided into serum and water, I believe. Don't quote me on that one. I can't remember at the top of my head, but serum is definitely part of the plasma. And then you've got your red blood cells, RBDs, RBCs, technically called erythrocytes. And then you have your white blood cells are in there, called leukocytes. And also platelets. Okay, these help heal wounds. Platelets. These are actually cell particles of cells that will clog. That's actually what causes the scabbing. when you get an open wound. Now, plasma is loaded with proteins that travel throughout the body if it's needed for various reasons. Okay, so, all right, so let's say that we've got protein molecules in the plasma. Okay. Now, on the outside, you have interstitial area. Interstitial basically just means it's between the cells. Okay, so on the outside, if you're not getting enough water, the water from the inside will actually start to leave. No, that's not right. All right, the top of my head here. Let me think about this for a sec, guys. Okay, you got the artery. You got the plasma proteins going through the artery. So if you're undergoing dehydration, the water, it will pull the water out. And then, okay. Shoot, you know what? Don't quote me on the exact process of what's happening here. As far as how it occurs, what you're doing to yourself. I can't remember if it's you're dehydrated or there was something else going on. But essentially what's going to happen though is the water, because of the difference between the concentration gradient, water is going to leave and it's going to literally flow to the point of the lowest point of gravity. And this is why you see people that get really swollen feet. The water just settles down to the bottom and their feet swell up. Another thing that you can see is also with gas exchange. So carbon dioxide and oxygen. So let me see. I'm going to draw something down here. I'm going to attempt to draw something kind of weird here. This is going to represent an alveoli. See if I can spell this. Alveoli. That might not be spelled right. Alveoli are little sacs inside your lungs that are at the very end of the bronchioles. Okay, and that's where the gas exchange between oxygen and carbon dioxide is occurring. So when cells are carried from the body, they're trying to get rid of carbon dioxide. So a cell will have a lot of carbon dioxide, okay, that it needs to get rid of. And then, but you're also breathing in oxygen, okay? Let me draw this up really quick. Get a green here. Okay. So, I should probably do a little label here. So, green, we're going to represent CO2. Blue, I need a new blue marker, is going to equal oxygen. Now, oxygen exists as a bond, so there's always two together, so we always put O2. All right. So the red blood cells, I'm not going to draw it because it will get in the way too much, but these little sacs in the alveoli are surrounded by the capillaries, and inside those capillaries, the gas exchange comes from the capillaries, which is at the very, very end of the routes of your blood. It's the tiniest part. And that's where the exchange is occurring. It's occurring between the blood and the capillaries and the little sacs in the alveoli. So these cells here that are coming from the body that are loaded with CO2 will come up here. And because you breathe in oxygen, you will have a lot of oxygen on the outside. Okay. So, oop, I didn't finish this. Gosh, there's a new marker. All right, so the concentration gradient of oxygen is a lot higher than the CO2 concentration gradient on the inside. So what's going to happen is, all right, this is a little bit different because we're working with gas concentration rather than a solution. So these things are going to pass through the membrane, the actual gas atoms, okay? So oxygen is going to pass into it to equalize that, okay? So you'll start getting oxygen inside the red blood cell. And then vice versa, because the concentration on the outside all of a sudden becomes a lot lower, the carbon dioxide will leave the cell and be expelled out of your respiratory system. All right. So as you see, there's a lot of different ways osmosis pertains to the human body. A lot of medical problems that can occur if things aren't working right. Anyways, again, I apologize. This is an unprepared video, so there were some moments where I had to sit and think about it. If you have any questions, go ahead and ask in the comments, and I'll try and look into it. And thanks for watching.